Welcome to another new episode. Like always, today we are here with an exciting topic that will boost your knowledge. So, without further ado, let's jump straight into the main discussion.
Welcome back, everyone. I am so thrilled to have you here for another explainer. Today, we are heading to the very bottom of the planet to look at something massive, something moving, and frankly, something that is widely misunderstood. Now, if you've been on the internet lately, you have absolutely seen the terrifying headlines about the so-called Doomsday Glacier. You've seen the panic, the exaggerated timelines, the hype. Well, today, we're going to cut right through all that noise. We are looking strictly at the science, the data, and the actual mechanics of what is happening under the ice. We're putting facts over fear so you can walk away truly understanding this situation. So let's get started. What happens if a glacier the size of Florida falls into the sea? I know, it sounds exactly like the pitch for a Hollywood disaster movie, right? But this is a macro-level, physical reality that scientists are monitoring in real time. This is the Thwaites Glacier in Antarctica. And the reason we really need to answer this question is because this enormous piece of ice is actively sliding into the ocean, and it is speeding up. The stakes here pretty much come down to one staggering number: 10 feet. If the Thwaites were to melt completely all by itself, it would raise global sea levels by about 2 feet. But the thing is, Thwaites isn't just a solitary block of ice. It acts exactly like a giant cork in a wine bottle. And the bottle? That's the entire West Antarctic ice sheet sitting right behind it. If Thwaites breaks apart and that entire ice sheet starts sliding into the ocean, we're looking at over 10 feet of total sea level rise. That is literally enough to fundamentally redraw the maps of the world and put massive sections of cities like Miami, New York, and London underwater.
So let's meet this giant. And we have to get one thing straight. This isn't just a frozen lake sitting quietly. It is a monstrous, actively moving body of ice. It's 75 miles wide at its front. In some places, it's 3,500 feet thick. I mean, just imagine 3 Eiffel Towers stacked on top of each other, completely made of moving ice. Every single year, it dumps around 50 billion tons of ice into the sea. To put that completely crazy number into perspective, that's the equivalent weight of about 140 billion blue whales thrown into the ocean every single year. Because of this massive flow, this one single glacier is responsible for roughly 4% of all current global sea level rise.
Section 1. The Failing Doorstop. Let's dive in.
Now, Thwaites sits on land, but its front edge extends out over the ocean, floating on the surface like a massive raft. We call this the Thwaites Eastern Ice Shelf. To really visualize this, I want you to picture a heavy front door in a house. There's a strong wind pushing on it from behind, and the absolute only thing keeping it from swinging wide open is a rubber doorstop wedged underneath. The glacier is the door. The warm ocean water and gravity, that's the wind. And this floating ice shelf is our doorstop. As long as that wedge holds, the door barely moves. But if it slides out of the way, the door slams open.
And that brings us to a terrifying certainty. Robert Larder, he's a marine geophysicist coordinating the massive international Thwaites Glacier collaboration, put it this way. The last bit of ice shelf in front of the glacier is poised to disintegrate. It's definitely going to go. Scientists aren't guessing here, guys. They are watching this ice shelf shatter. In fact, another researcher compared looking at the satellite images to looking at a car windshield that has just been struck by a rock. There are cracks absolutely everywhere, and the entire structure is losing its integrity all at once.
Which brings us to Section 2, the accelerating collapse.
Scientists have spent years gathering some truly astonishing data points that prove the brakes on this system are failing right now. Okay, let's get into the data. Here's the first punch. Over a 2-decade period starting in 2002, a research team tracking satellite images found that the total length of fractures riddling the ice shelf more than doubled. It went from about 100 miles of cracking to over 200 miles. And these fractures aren't just popping up randomly. They're opening up in the absolute worst possible places, right where the ice shelf anchors to underwater ridges that actually help hold the whole thing in place. Here is the second punch. From the start of 2020 to early 2026, the flow speed of the ice shelf roughly tripled. It is now moving at over 2,000 meters. That's more than 1.25 miles every single year. A leading geophysicist who actually measured this data looked at the numbers and described them as, quote, frankly nuts. Look, when the experts who study ice for a living call their own data nuts, you know for sure we are dealing with something completely unprecedented. And the third punch is perhaps the most alarming of all. The land ice behind the shelf, so the ice actually sitting on bedrock that directly contributes to sea level rise, has sped up by 33%, Remember, the ice shelf's only job is to act as a brake on that land ice. So if the land ice is speeding up by a third, it proves the brake is actively failing. It's exactly like driving a heavy car down a steep hill and realizing you've suddenly lost 33% of your braking power. You're mashing the pedal, but you just aren't stopping.
But this is not just a sudden glitch or, a bad year. By looking at ancient mud cores pulled up from the seabed, scientists realized this retreat actually began way back in the 1940s, likely kicked off by a powerful El Niño warming event. In 1992, a rapid 12-mile retreat began. By 2002, the fractures were doubling. Today, the shelf is poised to completely disintegrate. This is an 80-year crisis that has slowly built up and is now crossing the threshold into a dangerous runaway phase.
Which makes this insight from researcher James Smith so impactful. He says once an ice sheet retreat gets started, it can continue for decades, even if what started it gets no worse. Think about the sheer momentum of that. It's basically like pushing a heavy shopping cart down a gentle slope. You only had to push it once, but now it's rolling entirely on its own. Even if the oceans didn't warm another fraction of a degree, this glacier has enough built-up momentum that it might just keep retreating anyway.
Section 3. The invisible attack below.
So, what's really destroying Thwaites? It actually isn't the sun or the air temperature. It is happening in pitch blackness, thousands of feet underwater. To figure this out, scientists quite literally melted a hole through 2,000 feet of solid ice. That is the height of a 150-story skyscraper, by the way. And they dropped the torpedo-shaped robot named Icefin into the dark ocean cavity below. What Icefin discovered was a vicious positive feedback loop. Step 1. Deep, warm ocean water gets pumped into the cracks at the bottom of the ice. Step 2. That warm water melts the ice from the inside, creating cold, fresh meltwater. Step 3. This cold, fresh water violently mixes with the warm, salty ocean water, creating swirling currents and massive turbulence. And Step 4. These spinning currents act like underwater hurricanes, pulling up even more warm water from the deep ocean and slamming it against the ice. This loop targets the exact structural weak points holding the shelf together, melting them up to 10 times faster than the flat ice around them.
Which brings us to the actual topography beneath the ice, introducing a bit of science jargon called marine ice sheet instability. Now, it sounds complicated, but here is what it means. Thwaites actually rests on bedrock that slopes downward as you move inland. Picture the inside of a bowl. As the glacier retreats down into the bowl, the water gets deeper. Deeper water exposes a taller face of ice. A taller ice face is heavier and far more likely to collapse under its own weight. When it breaks, the glacier retreats even further into even deeper water, exposing an even taller face. You see where this is going. It's an unstoppable runaway collapse once the grounding line passes a certain point.
Finally, Section 4. Reality versus hype and what happens next.
Knowing all of this staggering science, we absolutely have to contrast the internet panic with the real data. The hype says the glacier collapses tomorrow, sudden tidal waves wash over the coasts, and our cities are gone next week. That is completely false. The real science is that the ice shelf breaking apart isn't the sudden flood. It's simply the moment the brakes give out completely. Remember the floating ice shelf? Since it's already floating, when it breaks apart and melts, it won't directly raise sea levels. Just like an ice cube melting in a glass of water doesn't make the glass overflow. The real threat is that without the shelf, the massive land ice behind it can gradually, over decades, accelerate into the sea.
But please do not mistake gradual for safe. The reality of a slow, grinding, 2-foot sea level rise over a generation is quietly devastating. A 2-foot rise means normal storm surges suddenly become catastrophic. Neighborhoods that have been totally safe for generations will begin to flood annually. Underground pipes and subway tunnels in coastal cities will start filling with salt water from below. Coastal freshwater wells that communities rely on for drinking will get contaminated. It doesn't happen with a massive Hollywood-style explosion. It happens slowly, permanently wrecking infrastructure and displacing millions of people.
Which leaves us with this final thought. The giant isn't collapsing today, but its grip is undeniably failing. The science is clear, the data is verified, and the timeline, while stretching across generations, is already in motion. The decisions we make right now about where we build, how we adapt, and whether we prioritize actual facts over clickbait fear will define the future of our coastlines. So what do you think? Will future generations thank us for listening to the science, or wonder why we didn't? Thank you so much for exploring this with me today. Keep asking questions, keep looking for the facts, and I will see you in the next explainer.
How did you like today's discussion? If you have any questions about this topic, don't forget to let me know in the comment. Stay well, stay healthy.